So good morning to everyone, and thank you for coming. So before starting, let me ask you a question. How many of you ever hear about TRITON? My assumption is that everyone, because you're here for the presentation. So most of you, this is good. So what we're gonna try to do today is that we are showing to you a deep analysis of the TRITON malware. Not only how to reverse engineer in the malware, but we're gonna show like a detailed demo. But before going deep, let me introduce myself and also the other speaker here with me. So my name is Andrea Carcano. I started to do ICS cybersecurity a long time ago. I did a PhD focused on industrial control system cybersecurity at the beginning on the offensive side, and then I moved on the defensive side. And that was before Stuxnet, just to give you a little bit of timeline. I worked 3 years in a big oil and gas organization in the Security Operations Center, and then I founded Nozomi Networks, the company where I work for, and now I'm there as a founder and CPO.
Hi everyone, my name is Yunus Dragoni. I work as a security researcher at Nozomi Networks. I studied computer security in Italy, and I'm also a member of the Global Shaper community. Thanks for joining us.
Hi, my name is Marina Kratophil. I started doing industrial control system security together with Andrea long before Stuxnet and before it became cool. My specialization is physical damage, mostly offensive, but because I also come in from academia background, you can't be offensive without having solutions. So I also designed a lot of defensive solutions. I previously worked as principal analyst at FireEye on the ICS security and as a lead researcher at Honeywell.
Yep. So thank you. So now let's start to talk about what we're going to present today. So this is the agenda for today. We'll go through a general introduction, explain to you how was TRITON and what TRITON really did. So the second part of the presentation will be focused on basically try to understand how for an hacker could be hard or complicated, or how many resources are necessary to build an attack like TRITON. So that is really important, right? We see many presentations of other researchers trying to analyze how TRITON was built. So today we're going to show that you don't need to be a government, or you don't need to have tons of resources to build an attack like TRITON. So, and in the third part of the presentation, we will go through a real demo. So we're going to show like the attack really working. As you know, the attack was missing the payload. We create a payload. We injected the payload on a real environment, and we film how the attack was working. And the last stage, we do an analysis about how was the real consequences and why the TRITON attack didn't really work on this specific incident. So, but now let me turn the microphone to Marina for the first part.
So yes, so of course we cannot proceed to TRITON without introducing what are industrial control systems and safety instrumental system. Also because so that we all work on the same terminology and the same understanding what those systems are. So industrial control system, as you likely already know, it's an umbrella term for specialized purpose computing system and networks for monitoring and controlling the application in the physical world. And those applications could range from power generation, manufacturing, assembly line to building automation and agriculture. So, and similarly, when the attacker, for example, penetrating a financial network, his goal is in stealing money. Similarly, when the attacker penetrates an industrial control network, his goal, his interest is in disrupting a physical application. So typically industrial control systems has a corporate network, they have SCADA network, they look the same, but they already we consider them, those computing devices which already more related to the controlling physical processes, they typically called already as operational technology. Nevertheless, they both still computational devices, and people who deal with them, those are coming from background of computer science. And as soon as we move to the physical damage and to the physical application as such, we're already dealing completely with engineering science. So the closer we come into the physical process, the devices becoming more specialized computing devices, and we typically know them as embedded systems. And those are cyber assets which are actually embedded into the physical application. That's why the systems are called cyber-physical systems. And subsequently, this type of attacks is called cyber-physical attacks. So the goal of the attack is called the disruption. We know that in the mass media, typically this scenario will be represented as a big explosion. It looks very, very impressive. Actually, this is a photoshopped image of one of the real incidents. And the reason why these explosions are possible because cyber-physical systems are inherently hazardous. You have moving parts of the machinery, electrical hazards, flammable and toxic materials, fires and explosions. So therefore, all of these industrial physical applications, they have layers of protections to protect, first of all, humans from these hazardous situations to occur. But in general, we try to protect humans, environment, and the machinery as such, because losing the machinery is also a huge financial cost and also just part of the damage. So this is how the level, so what you know, like defense in depth and security, this is the same valid for safety. So this is the levels of protection in safety. So in general, you start like, if you start from the bottom, you try to design the process as stable as possible, as such, as a process design. But clearly the processes will always deviate. That's why we have control loops. It's the second line. So we have sensors and actuators, which we measure the state of the process, and then we have control algorithms, which we try to bring the process back within the normal operational envelope. But control loops also cannot continuously keep the process stable, and therefore there will be always an alarms, and therefore we have third layer, we have human operators, which will intervene whenever they basically will issue manual commands to bring the process back into the stable state. And when the human operators already cannot cope anymore, then we have a layer of safety systems. They could be of different types. It could be safety interlocks, could be safety integrated system together with a control logic, or it could be independent system like safety instrumented system. So typically safety instrumented systems you will be using in those environments where you could have this big explosion from the previous slide. So this is independent standalone system with sensors and actuators which acts upon detecting hazardous situation, and it tries to prevent it from happening. So this is the last line of defense, last. After that, if safety systems were not able to prevent incident, we already have an incident. Then the last hope is also, but we already have an incident. We still can have like rupture disk in the design of mechanical vessels, for example, and some release valves, like mechanical valves which just like open by their own, but we already have an incident. So therefore, safety instrumented systems are important. And modern safety instrumented systems, they are software-based systems. It means they can be exploited. Therefore, since they are so critical to preventing casualties, for example, best practices suggest, and now especially since we know that there are threat actors which target an industrial control system, there is a strong recommendation to keep them on a separate, either on isolated network or in a well-segregated network. However, safety instrumented systems are frequently connected to the main control system, basically process control system. For data exchange, you then can compare data. For ease of maintenance, for convenience, low cost. Like, for example, there was one of the previous year, there was incident where the operators has lost entirely the DCS, and they could quickly switch to the SIS, and they were still controlling the process via the SIS because they lost networking access to the DCS. So, and also whenever you have like situation of the multi-vendor, so your main control system and safety systems of different vendors, then it's more difficult to segregate them, and they typically have some connections between each other. So as you could understand by now, that attack on a safety system will cause the most damaging outcome possible. And this was happened with TRITON. The attackers tried to install a backdoor on the safety instrumented system on the controller. So we consider it as a milestone in the ICS security clearly because, you know, such an attack endangers the lives of the civilians working in the industrial facilities. So every large mass media, of course, highlighted this case, starting from the Wall Street Journal, Washington Post, and whatnot. So this is something like where it takes, like, let's say, the cyber war and this blurring age between cyber warfare and kinetic warfare somewhere to the next level, because cyber is becoming kinetical. So in a nutshell, what has happened, the attacker obtained remote access to the safety instrumented engineering station. With that, they obtain access, ability to communicate with industrial controllers. So, and they try to install, implant the controller. So what does it mean? So the attacker tried to inject a passive backdoor. Some people refer to this implant as remote access Trojan. But in a nutshell, it's a program which sits in the controller memory, and it allows the attacker to read arbitrary memory, to write into the memory, for example, your shell code, and then execute it. So basically what's happening, the controller is becoming your slave. So your wish is my command. Whatever you will tell me, I'll do it for you. Even though the TRITON implant lives entirely in the memory, because safety instrumented systems typically, like safety controls typically never rebooted. So the only persistence which the attacker actually needed to achieve is to move it into the part of the firmware, which will not be part of the memory, which will not be overwritten by the override of the control logic. We will go through the steps through the presentation, so I will not detail like right now. I'll pass it now to Andrea.
Yeah, thank you. Thank you. So now I think some of you recognize this logo out there, right? So when I started to do research on ICS cybersecurity, I didn't have all these amazing tools, honestly. So, and you know I looked young, but I started a long time ago. That was before Stuxnet, before you know, the ICS cybersecurity was fashionable, let me say. So before I go ahead, let me ask, how many of you really did research, you know, before Stuxnet, like, you know, 2005, 2006? 1, 2, 3, 4, probably 1%, 2% in the room. So, you know, in my experience is that when I started to do that, I remember I was working for the European Commission, and the goal was build a malware attack industrial control system. And of course, you know, I started to study, I started looking for information online. It was very, very hard to find any type of information related to the attacks. I don't know for you, Marina or Yunus, if it was the same.
Call myself geriatric millennial, you know, so at that time, yeah, there was no so much attack happening for the ICS systems, and the only document which was available was NIST standard, which I read like 10 times, and there was absolutely no documentation, was like no information, no YouTube videos, nothing. Google just did not index those files. They probably were there, but Google was not indexing them. So for example, to learn the program PLC, I have to give a lot of calls to Siemens asking for free classes. So I was going into the classes together with teachers to learn how to program PLC. And right now, so for example, if you know to the virus total, you can download the engineering projects with a Griff Confidential. You can download every single manual, all the training from all, like script, whatever you call it. You will get all the trainings from all major companies on industrial equipment. So you now have so much learning materials which was not available before. Yeah.
Yunus, was for you also the same?
I can say that I was the luckiest one between you, because when I started, I was plenty of stuff to deal with, to play with that. And for example, TRITON or other frameworks, there were really lots of stuff for have a, let's say, a good starting point in this field. Yeah, definitely.
So now, this is great. And why we are highlighting this slide? Why we're highlighting this topic? We're highlighting this topic because, as you can imagine, so the attack on industrial control system are become more sophisticated, but the skills that you really need for build an attack are, you know, at the end lower, because now you can find tons of information online. You know, even the TRITON malware that we're here to, you know, analyze today, you can find it online now. So, you know, maybe not like in most common website, but it's there. So mainly the skills that you require are less. So here in these slides, we will analyze, we will see the number of vulnerability discovered in the last period, in the last 10 years. And as you can see, in the last years, you know, the growth of the number of vulnerability discovered is growing exponentially. So, and that is not because, you know, these systems are becoming less secure in the last few years, but it's just because now the community is very active. Now you can feel that everyone, so probably some of you are working for, you know, industrial control system, you know, organizations, some of you are researchers, some of you are working for vendors, but now, you know, the topic is very hot and is growing.
And actually, because the systems are never been, of course, we know they never been designed with the security in mind. So a lot of also all low-skill researchers who just start in vulnerability research, they start with the ICS because it's easier. So for example, one of our dearest friends, Aaron Leverett, when he wanted to learn how is it web exploitation, he started with industrial switches to exploit and build web servers because, well, that's where all the vulnerabilities are. So that was his first.
Yeah. So now we talked at the beginning. So one of the goals of this presentation was show to you what an hacker really have to do if you want to build an attack like Triton. What are the steps that you need to follow if you want to build an attack like Triton? So first step, you need to gather intelligence. You need to gather information. So that's the first step. So I don't know how many of you, but usually I never read a manual. In the past, I never read a manual of every single product. I start to read the manual when I start to, you know, to be focused on cybersecurity, because inside the manual, you can find tons of information. So that's the first starting point if you want to attack any type of system. So the second thing is to build a shopping list. If you really want to attack an industrial control system, you need to know exactly an industrial control system for all the different points of view. So build a shopping list with all the things that you need. So second, reverse engineering. As soon as you have all the reverse engineering, as soon as you have all the components, of course, reverse engineering is very important, not only about the software and the hardware, but also about the protocols, because you need to understand how to communicate with the controller. You know, as many of you know, there is a dedicated protocols for industrial control system. Some of them are proprietary, some of them are open, but you know, the most important things is that you need to understand that protocol. So now let's start from the first point, gathering information. So as I mentioned at the beginning, reading the manual is very, very important, right? Inside the manual, you can find tons of information. And how you will find a manual of such a system, right? So is a system not easy in theory to find? You cannot run in your shop and basically buy, you know, one TRITON system. How you can find it? So, and if you ever look online in any famous even website like a marketplace, you cannot imagine how many information and how many things you can find related to ICS controllers. So that is just an example. You need a TRITON manual, and you don't know anyone from Schneider, you know, you don't know how to get it. You can get it online with a small investment. So, and why is important? I don't want to, you know, deep dive on all the documentation that you can read and download it, but that is, for example, an important piece. If you ever did a reverse engineering of a malware, you know that you need to understand, you know, for which microprocessor was compiled that specific piece of software, if you need to do a reverse engineering. So where do you find that information? Do you need to open up like the physical hardware and try to identify which microcontroller or which CPU they have it? No, you just find it on the manual. So it's pretty easy. So, and the third point is which other resources you can use in order to find, for example, the engineering toolset. So as you know, every single device, like a controller, they need to have an engineering toolset. So the engineering station and in general, the engineering toolset is very useful because you usually need to build like a program and download the program inside the controller that basically that program explain to the controller how to act, you know, in the field. So, and where you can find that tools. So if you can start from, you know, basic channel, LinkedIn, maybe you have a friends that have that, you know, engineering toolset. You can ask to the asset owner if you know an asset owner that have that software, or you can look online and again you will find a lots of interesting resources that they give you that software. So for example, in this case, so for having the full complete toolset, engineering toolset for, you know, talk with the TRITON system, if you go on this Chinese website, I don't know how many of you recognize it, but it's very famous in China. Is Alibaba for $3. and we try it, right? Just because we were curious, we try it. For $3, they send you the completely tool set for, for basically talk with the TRICONX station. And was not that complicated. And, they even have more than one, right? They have many. So that is, how you basically can obtain, the software necessary to talk with the TRICONX system. So another important piece is the firmware. So as you know, these specific controllers are not running over Linux or over Windows, but they have their own firmware, and it's very important to get that firmware because you need to understand how the firmware is built. If you need to find a zero-day vulnerability, it's very important to know that firmware. Some of the other researchers in the community published a very interesting research on how to get the firmware by opening up the hardware. So they basically open physically the TRICONX controller and they extract the firmware. That was very interesting. The skills required for doing that is very high, and the risk is also high because if you make any mistake, you need basically to destroy. You risk to destroy the hardware. So that is one option to get the firmware. But as an hacker, you always want to try to be smart. So a way to find an hacker, for example, is inside the TRICONX software. There was basically already inside a set. Here you can see a set of all the different firmware version of all the different version. So there is probably 10 different versions. And so that was perfect. So no hardware hacking was necessary. It was easy. Download it, and for us it was easy to analyze it. So third part is on the shopping list is related to buy the physical equipment. You really want to build an attack like that, you need to get familiar with your physical system. So how you can buy a really TRICONX station? Where do you find a real TRICONX station? And again, if you look at the marketplace, doesn't matter if you don't have the direct contact with the vendor. If you look at the marketplace, you can find a lots of interesting material online. So here is just an example. All the piece that you need for build your own base, the TRICONX station, for test all this type of equipment. And as you see, the investment is not that crazy. Even if you ask an approval of that budget, if you want to build your laboratory in your company, it's not crazy. Probably, your CAO or your CISO probably will approve a budget like that. So, that's just an example for sure. It's not. So I saw many articles saying for build a malware like that, you need like a high investment in terms of time, in terms of resources, and also economic resources. But I don't think it's the case. So that is an example. So the third part that is very important is the reverse engineering. So, Younes?
Okay, let's have some fun, guys. So first of all, how many of you have already played with this engineering software? There's quite a few, no one? That's good, okay. So we started to focus our attention on the main engineering software, that is the TRIStation 1131 version 4.9.0. And we started to focus on the different DLLs and files that you can find inside of it. And if you just look at the image, you can see that from the description of each file, you can just extract lots of information. So you can, let's say, reduce their scope and analyze the necessary files that you think more useful for your main goal. One of the examples is we focus our attention on these particular configuration files that if you just parse it properly, you can obtain all the different models that can work in a TRICONX controller. Okay, so just some information that you can extract quite a bit easily, or other information that we were able to extract from the engineering software are also based on the concept of the user credential that are related to each project. So each project is related to a specific default credential, but you can also, and obviously those credentials you can find it in the manual, sorry. And you can also change this default credential with custom ones. If you have several operators that's working group, you can split the project based on their needs. And as soon as you try to log inside one of those projects with the wrong username or password, obviously, you will come up with this error message that you're not authorized to open this project because your username is not present inside the project. But what if there's a way?
Yeah, so very quick here. So that was an important finding of our research. Was never disclosed until today. So we're disclosing that also in according directly with Schneider Electric. But if you start to do reverse engineering as we did, basically we identified that there was a users embedded inside the system. This is a super admin users that basically have the ability to show a very nice, interesting menu inside a TriStation. And that is the menu. You can see how it's called the menu. So you just need to know that user and that password, and basically you become a super admin of the TriStation. And even if you have any type of project protected by password, with that user, you will get all the information. You need to have a debugging message. As you know, with this menu called backdoor, you can basically see all, you can basically activate any debugging message, any message very useful, if you are an hacker. So just to be clear, there was no connection between the TRITON malware and this menu. So there is no connection, no analysis that we see. We didn't find any connection, any proof that the attacker knew about these users. But of course, as you can imagine, as an hacker, now you know many of information. So we decided to don't disclose the name of the user, just to don't give information to eventually hackers that tomorrow want to do some bad stuff on our safety system. And this is just an example, right, about how many information you can get if you are that user and if you activate a couple of that flag that you see in the backdoor menu. You can get tons of information that are very useful for the intelligence of building that malware. So now let me say, of course, we are working in collaboration with Schneider, and it's very important to say, first of all, there was no connection between the attack and this finding that we found. So this user is active and hidden until the version 4.9.0 of the TRITON software. That is an official statement from Schneider Electric that basically they claim that from the version 0.1 was public in the manual. That these users was there, and in theory, in the latest version of the TriStation software, the users is not anymore there. We didn't test it, but that is what Schneider declared about the specific users. So now let's try to move very quick on the last point, that is reverse engineering of the protocol. We talk about how to gather information. We talk about how to buy the equipment. We talk about how to do the reverse engineering of the TriStation software needed for communicating with the TriConnect system. The last point is that we need to understand the protocols. So do the reverse engineering of the protocol.
Yeah, and mainly we need to be able to speak the same language of our target. Okay, so for doing the reverse engineering of the protocol, mainly if it is a proprietary one, you can have two approaches. You can start from ground zero and losing your head in raw data and using washer, stuff like that, and trying to understand each bit, the meaning of each byte. Or you can also here following a more smarter way. So you can focus on some of the DLLs that are present inside the workstation. And I don't want to drill down too much because also Farai and other guys, they already done an amazing job on understanding the similarities that you can find from here, for example, the strings that you can find in one of the DLL and the similarities that you can find in one of the scripts of the TRITON. So they clearly extracted those information from this type of DLLs and files in general. So you can extract lots of information, and obviously also here you have to reduce the scope because the final goal is not to have a complete protocol parser, but to have the necessary understanding for developing your malware. And based on all that information, we were able to develop our own dissector. So it's already available on GitHub, so feel free to improve it, download it, play with it. You can do it whatever you want it. And based on that knowledge that we gained so far, while we were trying... Okay, while we're trying to understand some part of the protocol, we also develop a TRITON honeypot that we are going to disclose after these days. So you will find more information when you try it yourself. So I don't want to spend too much time on how this script works because I want to give you I want to give you all the fun for trying to understand how it works. But mainly, it can give you a lot of information and could be quite a bit useful for several reasons.
So before we move to the most important demo, how TRITON works and how the damaging payload could look like, very quickly, what it consists for. So as a typical implant, it is multi-stage. So there are, at the beginning, in the first stage, which is argument set in shellcode, that attacker is making sure that they're in the right version of the firmware, which is a vulnerable version, and they're able to operate in the controller memory they can execute. In the second stage, they actually they escalate privileges so that they will be able to write actually backdoor into the memory, and they actually corrupt the memory to make sure that they change all the pointers to the right places. The third stage is a backdoor as such, and this is where the incident was uncovered. And the fourth payload, according to the public sources, it is a missing payload, which was like the damage payload was never introduced by the attacker. So in the first stage, the attacker searches the RAM of the memory until it finds the control program status structure. And actually, in that structure, the attacker is looking for the fstat field and try to change its value. And it actually could be any value. And as soon as if the attacker is successful, they understand that they're in the right version of the firmware. So this is how it looks like when you look at this at the protocol layer. So the attacker is searching for that fstat field, and the default value is actually 0. And then the attacker is trying to change that value into 384. And it's a random number. It could be any number. Just with that, the attacker is declared that they are in the right memory and they can be executing in the memory. So the third stage is, the second stage is injector. So, in this part, so basically what's important to know that inject and main, they actually injected together in the following structures you see on the slide. And the injector specifically is also looking for the machine state register, which is specific to this PowerPC processor architecture. With that, the attacker is trying to escalate privileges by writing specific value into specific locations. And the attacker needs to escalate privileges so that it could actually write IMAIN, it's basically relocate IMAIN into the specific firmware memory where they did not have rights to write. And as you can see, that IMAIN is between two values, 1, 2, 3, 4, and 5, 6, 7, 8, 9, 8. The attackers need these numbers to find the IMAIN in the memory during the injection, and then to relocate it into into the safer part of the memory. So, and then with that, the attack, their backdoor is becoming part of the firmware. It actually reacts to get MP status function code. And so basically, the attacker is modifying the handler of this function code, of this function code, so that it will be pointing to the IMAIN, to the backdoor. It also patches the memory so that, because there is continuous verification whether in-memory firmware and on the flash drive is the same. So it patches so that this verification will be always successful. So the attacker obviously, so the codes of the TRITON malware, they contain tons of debugging messages, which shows that the attacker tried so many ways to inject that backdoor into the firmware, and they were often unsuccessful. And they had a debugging message for every unsuccess, so basically for every edge case. So this is how it looks like when you execute the TRITON. So now we move to the demo, TRITON in action. And how many of you remember that after Stuxnet, a couple of companies was showing the experiment with balloon, to explode the balloon? Anybody remembers? Yes. So we just, to kind of compare the Stuxnet, and in the honor Stuxnet, we decided to go with the same experiment. So this is our testbed, how it looked like.
We mainly have our TRITON controller, so a low density chassis with the necessary models. And we have also our terminal panel that is directly connected to the Marshall connector, and at the same time is connected to the field device that in this time is a compressor that is connected to a balloon and has to control the inflation-deflation phase. Okay. So the safe logic that it is inside the controller is mainly created by a simple counter that has to control and check when you have to inflate the air inside the balloon and when you have to deflate. So the safety value is when the counter is reached the value 28, the inflation phase is it hands and it starts the deflation phase. Okay, so what if we were able to change that counter with a huge negative number so that it never reached or it took too much to reach the value of 28 and it restart the process?
So in this case, as Jonas was saying, you know, is a basic example, but that's actually show you how the safety system are important. And which type of information basically they are protecting, or which type of the process are protecting. So and of course, you know, you need to imagine that the balloon could be any type of other critical system that can create a huge damage. As Marina said at the beginning, remember the safety system is the last barrier that you have on a critical infrastructure. If you're able to act the safety system, you're done. There is no any other limitation on prevent any disaster.
Completely agree, definitely. So here we have our first setup though. So this is the engineering software. So the first thing that we are going to do is to upload this logic, this safe logic inside the controller. And at the same time, let's suppose if an attacker is sniffing your network. So it has already a foot inside your IoT network and it's able to sniff the process of the upload of the program. Or let's suppose if an attacker has already been able to enter inside your engineering software and extract directly from that the program. Okay, so this is what we are going to do, and based, for example, on the sector that we were able to develop, we can focus our attention on that specific program so that we can extract that program and doing further analysis. So doing further analysis and find a way for corrupt the entire process.
So what is the lesson learned here that is very important? The lesson learned is that if you are an attacker, you need to understand the program, right? You need to find a way to get the program, to understand the logic.
Exactly. So now let's start to speak some PowerPC. Okay, so we have the target program. We can dissect it with IDA, and based on all the information that we gained so far from the manuals, etc., we can dissect and analyze the program in let's say in a friendly way.
So if you remember, sorry, Eunice, at the beginning, we basically show how much was important in the manual to identify the microcontroller. That is the key information, because now we can reverse engineering the software that was uploaded, you know, thanks to specific software, because we know exactly for which microcontroller was compiled that program.
Exactly. So now that we were able to understand the exact offset in memory where the variable, the counter, is located, we can, here you can see the injection phase of the malware, and we have to take in consideration that information that we were able to gain previously, okay? So as soon as we completely inject the malware inside the controller.
So this is the injection of the TRITON.
Yeah, this is the real injection of the TRITON. And as you can see lots of debugging messages that it keeps the track of the status of the injection, okay? So, and as soon as we have our malware inside the controller, we can try to disrupt the industrial process. So, firstly, we will run the program from our engineering software, and we firstly run and see how it works properly. Okay, so how it works the normal program. Okay, so here we are connecting to the controller. and we are running the program inside of it. And on the other part of the screen, you will see, and in the meantime, sorry, we are also watching that specific offset of the memory so that we can check the value of the counter. And you can see that this is the normal process, so the inflation of the year and the deflation phase, and the value of the counter is normally in the range that we specified in the project. Okay, so from now there's nothing strange. From the engineering software, you can also monitoring the value of the counter directly from the software itself, as you can see. So it's all normal, nothing strange, and as you can see, as we watch, the value is acting normally. So what if we start to change that value with a huge negative number? Okay, so now we are ready to run our script, so use the property of the malware for changing that value. And as soon as we change that value, as you can see on the second terminal, you will definitely see the change of the current value. That is a huge negative value. Okay, and this is for continuing the inflation phase for really lots time. Okay, so we find out that this is really a die-hard balloon, so we have to accelerate a little bit of process. So, but the meaning is simple. Okay, so, and the meaning and also the consequences are simple, because at the end we will have an explosion of it. Okay.
It's unbelievable as you can imagine, how hard was that balloon.
It's really that hard.
It's not exploding.
Definitely. We discover late, okay? Definitely. So this is a possible consequence of an attack, but we have to prevent this type of issues before being able to protect him.
Yeah, thank you, Yunus. Thank you for the demo. So as you can see here, that was a real injection. So it was like just the payload injected in a real malware, and we basically show a demo. Now let me go a little bit quick here. So what we did also, we realized that we gain a lot of knowledge as a researcher about this malware. So we decide to actually publish some of the things that we did. So here you can find, three main tools. So one is the passive dissector. So how to basically discover if there is a TRITON infection, happening. So the second part is something that we developed also in-house, but also Schneider, for all his users, is publishing a specific tool active to identify if your TRIConnect system is infected. And the third one is an honeypot, actually simulate an entire TRIConnect system. Download it, play with it. Please feel free to improve it or just contact us if you want to know any other information. But everything is public on GitHub. So very quick on the detection. So the detection phase basically is based on the fact that the TRITON malware is adding a specific signature. I don't want to enter in the details, but is adding a specific signature on the payload when it's basically uploading itself on the TRIConnect system. And basically we can identify, we know how the signature is calculated, and we can identify it. So, but if you download Wireshark and you play with it, you will see basically, we actually publish it on how to identify it. So now to summarize, let me leave the stage to Marina.
Well, quickly, you probably noticed that we just tried to follow the attacker steps about like how would we build an exploit like TRITON, and we extensively tested it. It works like magic. So we had, as our model, we had a singular main processor. In any industrial facility, you will have a triple redundancy. The malware works, so it's unclear why the malware has failed. And then we develop a lot of tools to dissect the protocols, to detect the malware. And so interesting was, of course, is also to understand why the malware could possibly, like the malware, we're talking about TRITON, why the attacker has failed to inject the TRITON. And so there could be multiple reasons, but one of the possible reasons is that they actually were not able to deal with the plurality of main processors. So one of the big parts, so TRITON X is a very complex firmware. There is a lot of firmwares inside of other firmware, so there are a lot of smaller parts of the firmware. Like one of them is LSX, and it is actually patented technology. This LSX firmware is actually responsible for taking the control program from the engineering station, pass it to two other main processors. It executes control logic, and it's also responsible for synchronization and for voting for consistency between three main processors. It's a patented technology, and it appears so. For example, the attacker, as you can see, there have been a lot of debugging messages, and the attacker was able to basically, they studied every single possible case what could go wrong. There was not a single debugging message related to monitoring consistency between three main processors. This is likely because that would require so much more additional engineering effort, and maybe there was a misjudgment how much they need to reverse engineer versus implant stability. So to conclude, like why, like possible attacks objectives, like clearly just for a simple shutdown, it is too expensive exploit. You would never do that. Physical damage, most likely the attacker wanted to probably suppress safety actions during the actual damage attack. It could be also what we call like hacking Olympics. Is it like test capabilities? Can I do it in a live environment? As you can see, things in live environments can go wrong. It could be also a live drill. It could be like one of the possibilities extortion, because like if you also introduce already the force payload into the TRITON controller, and even if you later lose your remote access to the controller, that payload can be triggered at a random time, and then you go to the victim and say, hey, something goes wrong in your facility, I can fix it for you, and then it's easy, could be for economical or political pressure. So one of the so basically, what are the most important implications of public code becoming TRITON code becoming public? Clearly, it's become the motivation for other threat actors. It's raised the bar, this move forward, this red line, and so on. But it also the positive side that alerts industrial and critical infrastructure organizations to include safety instruments system into the risk assessment. And the most important, and this is where the message which we wanted you to take home with you, is that the moment is now to start creating auditing and forensic tools for embedded systems. Right now, asset owners have no tools to determine, is my device potentially tampered with? There is no auditing tools for that. There is no forensic tools. Like even if I establish that my device is probably tampered with, what has happened to my device? And there is no third party or company which could create those tools, because all the devices are so proprietary. There is such a huge diversity. It's really vendors who have to create those tools. We know that, for example, TRITON motivated Schneider to develop those tools. Now you can download them if you're legitimate user of the asset owner of the Schneider devices, equipment, you can download those tools. But if you an asset owner, go to your vendor and start this conversation right now before this malware became mass scale. And this was the end of our message for today.
Thank you.